Yeah, so the title of my talk is Computational Noise Resiliency in Deep Learning Architectures. And I'll just go right quickly. Put this slide together after yesterday and just kind of give it a reference point to what I'm trying to talk about. Yesterday, Dr. Pickoff from Rice talked about neuroscience kind of perspective, statistical view, noise correlations as a means to look at how we want to model some of these learning systems. Dr. O'Reilly from Colorado Boulder talked about autoencoders, error-driven thing. This presentation kind of extends it a little bit. I'll cover some of the notion about deep learning and how you handle noise as a means to improve some of the performance, but also kind of add on to it saying that the hardware design itself can be noisy, and it's as a means to get some of the scaling that we want. So this is a slide just to talk about a reference on how it connects to everything that we have. With respect to the outline, I want to talk a little bit about applications, how a noise is handled there, right, as part of the input data. And then add on to that, with respect to the algorithms, how in deep learning, leveraging noise in training, that actually we would actually inject noise into the training itself to add robustness, and how do we handling that. And then the extension to that is, if we're using noise and leveraging noise in training, addressing noise in input data, I'm supposing that and conjecturing that even the hardware itself can be noisy. We don't have to design something that's guaranteed to flip between 0 and 1 as a transistor would today. Right? So that's the kind of outline that we have. I have 1 or 2 slides on SRI. I'm trying to minimize time. SRI is a nonprofit organization for Stanford Research University based in Menlo Park, and we do all good stuff. Right? I'm actually based in Princeton, formerly the RCA Lab, Sarnoff Corporation, but fully integrated with SRI. We do all things computer vision and machine learning. We built ASICs as well, a lot of kind of applied computer vision in many different areas kind of listed there. Okay? I think the differentiating thing we do is really vision in extreme condition, very low light, high motion, GPS denied, very tough kind of situations. And I'll show you a couple of examples there. So I want to talk straight into the applications, right? Here's an example where you have a night vision system and you want to get good imagery from it, right? But as we know, in low light, the sensor itself is photon starved, right? This is physically not enough light hitting the sensor itself. You get a kind of noise. Now what I've shown here is some processing they've done, non-learning, non-neural-inspired. But in that sense, we're looking at temporal data to get some of the kind of noise filtered out, right? And I'm also supposing that there's some neural kind of activity with respect to deep learning where we're doing in-painting, right? Looking at how we learn over a set of images, and then from the noise reduce it, because now you can paint over some of that noisy data itself. What this differs from a lot of things that we talked about today, where we say, neural-inspired, what kind of applications? And you say, well, we're drowning in data. This is the opposite. In this sense here, the signal is insufficient, but based on your statistical information about how the scene looks like, edges and things like that, you can actually fill it in, right? So an inference of what the images might be. So I think this is almost the opposite of kind of data drowning, that I think kind of neural-inspired kind of applications will work well in. Of course, the traditional kind of wide area surveillance, we work a lot of this. I think Dr. Hawkins talked about the kind of GPS type applications. In this case here, we actually do visual-based tracking, the small 5 to 8 pixel kind of target, and lots of vehicles moving around. But also looking at how they're driving, some of the, is it passing to a checkpoint, is it making kind of strange patterns and things like that. Those will become an alert. We want to put that on board. And the UAVs are getting smaller and smaller. They want to have more capability or kind of longer flight times. So power is definitely an issue. So those things that I think folks have covered. Further than that, we're actually doing a lot of work where we infer, based on the tracks and how things are moving between point A and point B, what does some of the location mean, right? For example, if during lunchtime period, everybody goes into this location, you can deduce probably it's a restaurant or something like that, right? So those kind of inference over time, we can actually make, impose what that might be in terms of a location, so infer entity and also locations based on that. So a lot of that work done with ONR, but a lot of learning kind of things as well. And in those cases here, we have to do both spatial and temporal kind of analysis, right? And I think those will be very good for kind of newer inspired kind of things. The traditional kind of detection and tracking, we do that. What we show here is, a traditional pipeline shown here, but with kind of deep learning, deep convolutional kind of approach, we can get kind of one order of magnitude performance in terms of the tracking by actually learning what a person might look like, right? So those are kind of traditional applications that work well as well. There's other applications, I'll go through this quickly, where we look at kind of big data sets, right? So the intelligence community would be interested, where you have a large collection of data, but you want to know what's the theme around it, what are the big kind of thematic items that might be there. We have gone through a couple of approaches. One, it would be you define classes, and then we go in there and segment and index them. And the different bubble size kind of shows what kind of, for this data set, what are the big themes. Well, we also actually use some learning approaches where we say, well, I don't tell you what the classes might be, but you discover what they might be, and they'll come out and pop out. And the notion here is that will help the analyst down the line to say, these are the big themes, you should actually go down and dig deeper into it. We also looked at other applications here, for example, where we do multimodal type of behavior analysis, looking at gesture, but also facial kind of recognition. So the human computer kind of interaction, where I think will be interesting as well for kind of new inspired applications. Okay. I do want to get to some interesting kind of things that I can show. Some of the videos I can't show, but this one I talked a little bit about for NIH kind of funding, much like what I talked about in terms of the image classification. For NIH, they want to know what is the calorie intake, right? When you go to the restaurants, am I eating too much and things like that. So this is an interesting one that I thought I could show. We over a set of trained, I think about 10 plus kind of classes, what type of food. What I don't show here is that we actually have another means where we estimate the volume of food, right? So there's we have a single camera sweep on a mobile phone, look at what the volume might be. In this case here, if you put an app to interface to the cloud, where we have all the kind of learn classes, and you kind of deduce, okay, this is mixed fruit, and this is kind of fried chicken, and you kind of give you additional information about calorie kind of intake, right? Green salad and things like that. What I didn't have them do is actually point to the more guilty food, right, like chocolate cake or something like that, where I think it would be more interesting. Right? But I thought this might be interesting to kind of show where, okay, you look at some of the learning systems that are out there, not looking for cats and dogs, but this might be interesting for folks. Okay, so back to what I was talking about, noise in terms of input data. So, some of the generic thing like poor lighting, right? Where you have a kind of Bayer mosaic on your sensor. At low light, you're going to get a lot of these kind of noise, kind of artifacts from just not enough photons hitting the sensor. So poor lighting can induce kind of color effects. And as I suppose what I talked about in the beginning, an inference kind of engine actually can help remove some of the noise better than what we can do with filtering. Because filtering looks at near neighbors, and some of it you can't deduce, right? You can't lose a lot of signal from just straight filtering. Of course, motion, noise, blur, and things like that is another source of noise. And then, of course, kind of dynamic range where, direct sunlight and things like that. If I go a little bit deeper and say, what are the sources of noise? And this is a canonical processing pipeline from capture, enhance, segmenting it, getting the feature, and looking up a database. There's a range of kind of noise that we deal with. I talked about signal noise, motion noise. There's even processing noise, whether it is floating point, double precision, those kind of things, the type of feature strength, how strong is the algorithms, and how you model it, right? And really, what I wanted to get from this slide and talk about is really there's a lot of data redundancy that you can leverage, spatially, temporally, and I added a little bit more kinetic and modeling from the perspective of you can model how an object moves within the scene. If a car is moving at a certain speed, and you detect something that is walking, that you think is a person, but is walking and walking, quote unquote, at the speed of a vehicle, is probably not a person, right? Those kind of things you can deduce as internal results. So there's a lot of redundancy that you can leverage that in the processing today, in some of the vision applications we deal with. So we understand now applications and noise and how we deal with it. So let's look at kind of deep learning kind of systems and some examples. I just have a couple of slides to talk about some examples where we actually use noise to improve the performance. Right? In this case here's a paper, Vincent et al., where they have kind of stacked autoencoders. They're going to train each layer individually and then stack it up. But for each layer, they actually go through a process where they stochastically corrupt the data. So if you have input X, you would actually corrupt it, maybe lose a few bits here and there, go through a mapping and get Y, and then you reconstruct it to get Z. And then you have a kind of loss function to see how well you do when you reconstruct. Right? And for each layer, you train it. And then once you stack it up, you get actually a better performance as shown here. I don't have the numbers here. But each layer, in a sense, can be denoised and then stacked, and that improves the classification process. And these are very recent, 2010, and there's even a 2015 under review paper where they said, well, rather than doing it one stack at a time, how do you heuristically do the entire one and kind of get between layer performance, right? So this is interesting, right? We understand now applications and how we deal with noise, but actually in the machine learning environment, we actually now interjecting noise in it as a means to improve performance. And if we don't stop there, there's other means. Here's a paper from Hinton in 2012 where he has a procedure called Dropout. You have a big, kind of very deep network, but he is purposely, for each input, randomly omitting some path of it, some trees and things like that, as a means of kind of reduce overfitting, right? And he's shown that for there, you can actually improve some performance with somewhat dropout right here. And without dropout, it's not, there's a higher kind of level of error. And then we're working also with Professor Benjio at Montreal, where he's looking at corrupting the noise within his network in the backprop kind of thing, where he's also improving performance. Again, interjecting noise in there so that your layers within your deep belief networks are tuned well. So here are two examples in the machine learning community where noise is actively used, right? So I've talked about applications. I've talked about the machine learning side in terms of using noise. So let's talk a little bit about hardware, the last kind of piece of the puzzle here. And I showed this slide with some data from Eugenio from Purdue. And don't worry about the exact number. This is a little bit dated, but he had implemented the kind of ConvNet pipeline in Intel, NVIDIA, and even FPGA. The point here is that, yeah, there's a lot of neurons, a lot of parameters, a lot of connections, and I think Paul talked a little bit about that previously. Is deep, and there's a lot of dimensions, right, to it. But what we want to get to is that there's a high level of performance that we're trying to hit, but what we want to desire is to get to like a 2-watt kind of solutions, right? So if you just look at relative numbers, it's about 250x performance and power and speed up. So you can't just wait on Moore's law, even with whatever scale version of Moore's law there, to get to kind of these type of performance. So what can we do? Now, from the scaling perspective, in terms of how do we get there, we know that, and we talked about the high compute and interconnect density. I've shown an example for just the ConvNet perspective, 65K neurons, how many connections here, millions of connections, quite a lot. And if you looked at kind of spatial temporal, if you want to look at temporal analysis, right, a lot more memory than you need. And interesting enough, what I didn't talk about in the last slide is within the ConvNet kind of architecture, everybody's using it. Recently in a CVPR paper, they try to push video through it, right? At the image kind of analysis, they get maybe 80, 90% accuracy. But once they start pushing video to it, they get down to 60%. And I asked the author, why? Why is that, right? And part of the reason is the convolution net is not designed for video, specifically that. And he's, in a sense, learning the camera motion and is throwing off some of the results. So a spatial temporal model will work much better than just pushing things for something that's not designed for it. So we know that if you look at spatial temporal analysis, a lot more interconnects in memory. And these type of interconnects that Paul talked about, high fan out that's needed. So we talked about power. Paul talked about that as an issue. I will actually suppose that noise would be an issue. You think about these very dense packed silicon, right? A lot of nodes, a lot of interconnects. It's bound to have some failures here and there. Right? Not only just yield, but dynamically, there's going to be some effects. So noise will be a key issue. Why didn't my network work the way it is? Well, it's tightly packed, and there's some chances that it would fail. We've seen that in big clusters, in big machines today in data centers. And as we shrink that into a die size of multiple die, you're going to have those kind of effects. So what I want to suppose is, can we design an architecture that is itself noisy, right? That the connections are noisy, that the memory is low precision as a form of noise. And what are the trade-offs, right? Can we build something that is inherently noisy, but let the algorithms handle it? We know that, yeah, there's a lot of data that we train against that helps performance. There's means. We're actually using noise in terms of our training. Can we leverage that and get performance at the same time? Now, if you look at the computing research and where they're heading, there's a couple of things that I noted. Near threshold kind of computing, approximate computing, fault-tolerant computing. I think it's all interrelated, where fault and noise, approximation and noise, those are all interrelated. From a kind of near threshold kind of perspective, here's a paper that talks about rather than operating, let's say, at 1 volt or 1.2 volt, you really want to operate closer to where the transition between 0 and 1 might be, right? That's actually the most power efficient area. But as you get closer and closer to that threshold region, the chances of flipping in terms of binary 0 to binary 1 happens a lot higher, right? So can we operate closer to there but manage it enough from the algorithm perspective, right? And I talked about the nanoscale kind of design issues. Not only the power density is going down, the transistors are getting smaller. How do you get it to dissipate enough power at such a small geometry? But there's other effects like dopant fluctuation. Can you actually dope a transistor good enough? Is there variation between transistors? There's aging effects and things like that as well that you can't really guarantee anything anymore in some of these nanoscale design. So I'm supposing that these new chips will be noisy, and can we handle it? Can neuromorphic kind of architectures leverage these pieces? And what I'm also saying is that the community, in a sense, trying to look at near threshold, approximate, and fault tolerance, are trying to compute, your Windows OS or your Linux kind of operate the normal computation, and that's where it's failing because, the traditional von Neumann storage architecture things. This doesn't work well for this kind of noise. You can't guarantee it. On the other hand, our sparse representation, distributed nature of HTM or deep learning kind of approaches allows for that. Right? It's okay one or two areas within your tree, your network might be in error, but collectively it will get you the correct results. So I think, on the other hand, we're looking for neural-inspired applications. I'll turn it around and say, I think some of these approaches works well with neural and go the other way. So this is what I wanted to get to. Now, I want to show some results where I've done some quick analysis to really say, some of the kind of Bose machines, Markov, random field, all those are inherently tolerant to noise, right? There's some noise immunity built into it. Part of the reasons is iterative, right? You go back and forth and you kind of refine your solutions down to an answer. So even though you have some perturbation in terms of how you are getting to that result, as long as you converge, that's fine, right? And it's iterative in that sense. So iterative solvers and things work. Now what I've done here is shown as a way of saying, do we understand noise itself? Is to take an image and for each of bit in the image, have a probability of a bit flip error, right? And say, well, once I have a probability of error, I want to now map it and say, what's the distribution like? What does the noise look like, right? And say, if we understand the shape of the noise, can we now handle it? And saying, conjecture that if we can control the noise, we can actually tolerate it in the computing. And just to say that, without any correction, if you just randomly say, each bit in my 8-bit image has a probability of bit flip, it really looks like a flat shape. Basically random, right? From one scale to the other scale, there's nothing. But as you fix some of the bits, let's say either in your MSB or your your upper 4 MSB, the shape of the noise kind of goes back to zero, center around zero. So you're tolerating some of the tail end. Some of the tail end noise around here, basically squeezing these back to the center. And that's why it works. You understand the shape of the noise. So what I'm saying here is that if we can design circuit, memory registers, or other components where we understand what the distribution might be, then we can actually leverage it, right? And this is another application I've done from more of an approximate kind of side and not learning, but it's a hierarchical kind of iterative search for image registration. And what we showed here is that for just input noise, this is your performance, right? Where if you have an origin image without any noise, you get some sort of edge detection for registration. Once you start adding noise, you don't see this, but there is some performance that you can get in terms of the bit flip probability here. And as you start saying, every time I've accessed some sort of local memory, I'm going to have a bit flip error, there's a range of performance capability here. And even at, let's say, at this 0.001, so this is 0.01%, right? So about 10%. I get about 1 pixel error for fine stabilization. That's not too bad, right? So I'm saying that you can actually purposely tune down your power, operate in the near threshold, get some power savings, leverage the noise, right, for this application. And I'm going to make one step and say, well, for some of the neuromorphic thing where you have the sparse representation, all that works as well. And if you think bigger and say, okay, what does it really mean to have noise in your design, right? I would say that the noise will actually provide an additional design knob, right? Today, all the tools for designing VLSI make some guarantees. There's some margin, clock margin, frequency margin thing, and we're basically over-designing some of these systems, right? And you can actually pull that back and say, if I understand how I'm going to be noisy, right, I can actually have a design knob. And that design knob offers you the additional scalability and as well as kind of additional performance as it builds some of this. And if you look at, from the neuromorphic kind of perspective, you can actually scale it. So think about a deep belief network, many hierarchies. I can afford, for example, in the lower layer to be more noisy compared to the top. So that's a knob where I can design. And how do I scale that? That's dependent on what you want to model. I also talked about, crosstalk. So we talked about interconnects, packet switching, and things like that, spiking networks. Maybe that itself is a form where if you have a design knob, crosstalk is actually afforded. You can actually handle and afford that. You can think about having a bus, let's say between point A and point B, a wide bus, but you might want to scale it differently in terms of the width because you might be more worried about the MSB rather than LSB, things like that. So that's a knob that you can design against. Let's see, and it's more that one can go into and think about what does it mean. And are we really saying that we're going into analog computing, in terms of really building analog circuit? I would say no. It's kind of a mix where you still want to design it in the digital kind of domain, but having some leverage in terms of what I mean in terms of noise and controlling that shape of the noise. So here's my last slide. I went through it quickly. I showed, again, applications, algorithms, and hardware, and how noise is kind of used, right, or leverage, right, from the application perspective, not only for applications that is just drowning in data, but also on the flip side where there's just not enough signal to play with. And I think neuromorphic kind of applications can help there. Then in terms of training, I showed some kind of deep learning examples where you purposely interject noise in there for overfitting and other issues, right, to get better performance. So we are actually using noise. The research community is doing that, and that's good. Then if you interject and say hardware itself, I think you can leverage noise. I've shown some example where I don't think it's actually that far off, right? The circuits themselves, because of the nanoscale kind of issues, dopant fluctuations, all those things will be here. It's much like Powerwall these type of systems are going to be noisy, right? And I think within this community, looking at noise and how you design it will be beneficial. That's all I have. Great, thank you.
So I have a quick question. So I really like this perspective, but one thing that I think the idea of using noise or having noise be something that in real neural computation, neurons aren't 32-bit precise, for instance, but you keep bringing up the deep belief networks, deep learning, and so forth, and those are networks, in particular the training, can be highly sensitive to learning rates and any sort of perturbations. I mean, backprop's a very sensitive algorithm, for instance.
Yes.
So what are your thoughts of, you're kind of going back and forth between what I would call neural computation, what I'd call not really neural, artificial machine learning stuff. So do you have any thoughts about where noise might apply to the training of artificial neural nets, like in the hardware level noise?
Yeah, I think so. From the training perspective, like I said, you could think about like interjecting noise. I showed that example. I don't think it's that far off. If people are doing it, it's still almost like a black art from understanding what each layer is trying to learn, the autoencoder kind of scheme. I think part of an effort that we are starting off soon is looking at how much training time you can reduce by some of these techniques, drop off and things like that, as a means of training.
But that's noise now at a system level. Now, if at a hardware level, if you change a high significant bit during a backprop algorithm, you're going to just jump to some completely other part of the parameter space, and who knows what would happen.
Right, and I think it depends on what layer you're talking about.
Okay.
When you're in the lower layer, I think you can afford more. Working with Dr. Bengio at Montreal, he's looking at kind of low precision weights where he's purposely reducing the precision between the weights and the connections, and he has shown it. I don't have the numbers or the paper reference, but he has shown that to help as well. So we're hoping to quantify that over a larger data set, because right now you can say, well, over this or over a data set it works. You really need to show it over a larger benchmark. So I don't have that yet, but we're looking into that level. Where can you trade off precision and at what layer? So that's my answer. I don't have a specific one, but we're looking into it.
Great. Well, thank you very much. I appreciate it.